So polynomial, power, and rational functions, obviously that's a lot of stuff. So in chapter 2, yeah, it's a thick packet, it really is. And we are going to split this into 2 tests. So we see here it says humidity and relative humidity are measures used by weather forecasters. Humidity affects our comfort and our health. If humidity is too low, our skin can become dry and cracked, and viruses can live longer. If humidity is too high, it can make warm temperatures feel even warmer. Mold, funguses, all that kind of stuff. Dust mites live longer, so anybody with allergies is going to have trouble with that. And it says later on in the chapter we're going to talk about how relative humidity is modeled with a rational function. So rational functions, hyperbolic in most cases. We're going to be talking a lot about hyperbolas in this chapter, but we're also going to talk about lines and quadratics with our parabolas and all that good stuff. So things we're going to do. Modeling using linear and quadratic functions, so figuring out whether or not we should use certain relationships to see if things are well, correlated with each other. You know, do these two things have something to do with each other? So, and it was in the last chapter, right at the end of the packet, where we had that list of all the applications and where you usually will use those functions. Modeling using power functions, polynomial functions of higher degrees, finding the zeros of polynomial functions, which we hope is factorable, but in some cases is not. Finding complex zeros, and that includes a little bit of talk about imaginary there. Using the fundamental theorem of algebra, which is a tiny little sentence that Gauss said that got everybody going and got several books on algebra going, and that is basically if there's an X in it, there's an answer. And everybody said, let's find all the answers, and that's math. That's how it came to be. So graphing rational functions, solving one variable equations, and solving one variable inequalities. So a lot of that, hopefully you're thinking, hey, I've done that stuff before. So we're just going to build on it a little bit. There it goes. So 2-1. This is where we're going to talk about just linear and quadratics and modeling today. So notice we're not talking cubics, quartics, any of that kind of stuff. Using polynomial functions and using linear functions, the lines, we will talk about average rate of change again, which is of course just slope. That's all average rate of change is. Using linear correlation and modeling, using quadratic functions and applying quadratic functions to real world things. So, it says, do you remember what a standard form polynomial function looks like? Give an example and explain. Take a couple seconds here and write down something that you think is a polynomial function. And go as basic or complicated as you like. I just put up a quick example up here of a standard form polynomial function. So the first thing we have to do is we have to know polynomial. Obviously, that's a definition. What on earth makes something a polynomial function? Well, if it has whole numbers for all the powers of the variable, then we're talking about a polynomial function. And then it's the standard form part that's really important to us, and that's that you always have your x's in decreasing power order as you go down. That's when it's considered to be in standard form. So in this one, I have the 5, then I don't have a 4 or a 3 for a power, and I'm down to 2, 1, and 0. So you have to know what a polynomial function is. And it sounds kind of silly, but the first part of your homework will be, is this a polynomial function? If it is, find stuff. If it's not, tell us why, you know. So we talked about that definition right off the bat for a polynomial function. Let n be a non-negative integer. I always think that's kind of silly. A non-negative integer, because the integers would be like -4, -3, -2, -1, 0, 1, 2, 3. And yeah, you want the non-negative integers. But you also could just describe it as the whole numbers. You know, the whole numbers start with 0, 0, 1, 2, 3, 4, etc. So what they're really trying to get at here, why they're saying that, is because they're reminding us they can't be negative. All right, they can't be negative for the powers. It doesn't work. So if we let a sub 0, a sub 1, a sub 2, all the way up to a sub n be real numbers where a sub n is not equal to 0, so we do have some kind of leading coefficient. What we want to notice is that the x's are going down by 1 power each time as we go through that. That's the standard form of polynomial function. So this is a polynomial function of degree n because we didn't see the actual numbers. We have variables up there. But we do know that n is the highest power that we see in this polynomial, and that's the degree. That's where degree comes from. You have the highest power of your polynomial function for the x's. The leading coefficient in this one, leading coefficient means just that. You know, coefficient is, it's a number that's working with a variable. That's the whole part to that. And the leading one means the one in front. Well, you have to have it in standard form so that you know it's the one that you go in front. So you always make sure you have your variables in descending order of power, and then you look for that first term, and the leading coefficient will be right in front of that. The zero function, f of x equals 0, is a polynomial function. Why is that important? Because that's the line y equals 0. And they're saying horizontal lines are functions. And for a second we go, duh, it's going to pass the vertical line test. Of course it's going to be a function. But it's special. And that's why they have to kind of talk about that a little bit separate, that y equals 0, it's actually the x-axis. It is special. You know, is there something weird going on with it? And the answer is no, except that we say it doesn't have a degree. Since there's no x, it's x to the 0 power. And it doesn't have a leading coefficient. So that's really the only thing special about it. So polynomial functions are defined and continuous on all real numbers, and we want to know what that means. That sounds like a lot of good gobbledygook, but what does that mean about polynomial functions? Nobody wants to take a shot this morning? If they are defined and continuous on all real numbers, what are their domain? All real numbers. Whatever you want into them. How about continuous? Do you remember what that means? It doesn't have a break. It doesn't have a jump. Fancy name for that was discontinuities. It won't have any discontinuities. No breaks, no jumps, no holes, none of that stuff. Which for a second we go kind of, thank goodness, you know, we're back to normal stuff. You know, there's nothing weird going on here. Relations are anything we can graph. Is every relation a function? Pretty obviously not. No, it's not. We've been graphing all kinds of relations this year, but we've had some that had breaks and jumps and definite discontinuities, so every relation is not a function. Is every function a relation? Yes, absolutely. You know, so not a thing that works forwards and backwards. If you remember your geometry, when you're flipping things around, you had to check and see it was the truth or falsity of the statement. This does not work both ways. So down here it says, which of the following are polynomial functions? For those that are polynomial functions, we want to state the degree and the leading coefficient. If they're not, then explain why not. So take a look at A. Function or not? No. What's wrong with it? How can you so positive? Is A a function? It is. It is. We see real numbers in all of those positions, and we realize that, well, yeah, 3, 1, those are whole numbers. So this is okay. This is a yes. So then we have to tell them the degree. What would that be? Yep. 3 is the highest power of our variable. Leading coefficient. What is it? 4. It is in standard form. You know, it's missing the squared power, obviously, but we have the highest power, the x in the first position, and then it is in descending order from there. All right, how about b? Is that a polynomial function? No. Does it say we have to tell them what's wrong? For those that are not, explain why not. What's wrong with it? We have a negative. Yeah, negative integer up there. So this is a no. We have a negative integer for a power. That's bad news. We don't want that. You could also just say, no, the powers are not all whole numbers. That would cover it as well. All right, C says we have this thing called, pardon me, h of x. And we want to know, oops, too far, whether or not that is a polynomial function. What do you think? Yeah? I want you to write it as a power. What would it be? What's square root the same as? 1/2 power. Is that a polynomial function? Nope. So we look at that and we're like, hey, we've graphed that before. That's got to be a polynomial function. No, it's not, because square roots, remember, they have like a starting place and then they go on forever in one direction. So this is a no. And that is because, like I said, 1/2 is not a whole number. All right, how about D up there? A different color. D is good? Okay. It isn't, exactly. So one of the things that we would do is either do this in our head or, you know, write it down in standard order, because they're going to ask us about degree and leading coefficient. So what's our degree? It is a 4. That's our highest power. Bless you. Leading coefficient? A -2. -2. So, like I said, 6, 8 of these in your homework where, you know, the objective is, do you know a polynomial function when you see one? So you want to check on those things. Okay.
What do you mean by half a polynomial?
Whole numbers are 0, 1, 2, 3, 4, 5, 6, etc. No decimals, no fractions. And when they say non-negative integers, that really is the set of whole numbers. So we can have y equals 0 because this is like y equals 0x to the 0 power. So that counts as a polynomial function because 0 is a whole number and it'll work. But if we have anything that we could see, hey, this is being raised to a power that's a fraction, a decimal, a negative, it's out. It's out. It's not a polynomial function.
Wouldn't it simplify to 3x squared plus 4x?
Oh, good question. So the question Kevin has is, since this is square root, couldn't we just write this as 3x squared plus 4x squared? What do you think? There's addition in there. We can't do it. We can do that when it's pure multiplication or division, but if there's addition or subtraction, it takes a lot more math to get that thing simplified. So we wouldn't be able to do that there, but excellent question. All right, all constant functions as well as the 0 function or polynomial functions. So they're saying horizontal line y equals 3. That's a constant function because 3 is a constant. There's no variable there. That's not going to change. So polynomial functions of no and low degree. The 0 function, which again is just y equals 0. That one, it is kind of weird because we say that the degree is undefined. You know? Even though you think of it as 0x to the 0, so the degree should be 0, it's special. So we say the degree there is undefined. But when we have an actual number, y equals 3, y equals -7, that we say has a degree of 0. Then, linear functions, little imaginary 1 up there. So that x to the first is what makes that a line. Mary, did you have a question or stretch? Stretch. Okay. Quadratic function, highest power for the variable is a 2. That's a quadratic. And that has a degree of 2. So, some basic and some not so. I know that we don't talk about this in Algebra 2, so that might be a new little piece for you, thinking about that special y equals 0 is undefined. But most of the rest of this, yeah, you dealt with this in Algebra 2. Here's the problem. It's so easy, we forget it. You know, the brain is a marvelous little machine, but when things are really easy, our brain says, I don't need this, I need to make space for harder stuff, and it dumps it, you know, it really does. So things that we kind of hold on to for a test and then maybe don't need it after that. Degree 3 polynomial functions will be studied in section 2.3, so those are our cubics. This section is going to focus on the properties and uses of linear and quadratic polynomial functions. And I think most of what we do today is just the linear. Yeah, everything we're going to do today is going to be the linear pieces of that. So lines. A linear function is a polynomial function of degree 1 and has the form f of x equals ax plus b. Now, what's the f of x all about? It's a function. You know, we want to show people, hey, this is special. It's not just y equals mx plus b. And you probably noticed this before on our calculators, that when we go into the linear regression right there, number 4, it says ax plus b. And that's the same thing here. And generally when you get into those AP courses, you start talking about it as ax plus b instead of mx plus b. But we know a is still the slope. That's what it is. So a and b are constants and a is not equal to 0. If we use m for the leading coefficient instead of a and let y equals f of x, then this equation becomes y equals mx plus b. You know? So we're backing up a step and saying, all right, we've talked about functions before where we didn't really have an equation for them, but we had a picture. That doesn't mean they're not a function, it just means we didn't have an equation for them. It's the same type of thing here. We can look at this function and say, hey, that should be a line, that should be y equals mx plus b. But maybe somebody's doing something a little bit different with it. But we're going to think of it as y equals mx plus b as we work through it. So, question here is, are horizontal lines linear functions? Answer that since I've answered that about 3 times so far today. Yes or no? Yes, they are called constants. Think about this one for a second. Vertical lines? Vertical lines functions? Why not? They're big time going to fail the vertical line test, aren't they? Because they're vertical lines. So no, they fail the VLT, vertical line test. So horizontal lines are functions. All is good. Vertical lines, do not. A line in the Cartesian plane is the graph of a linear function if and only if it is a slant line. That is neither horizontal nor vertical. So when we're graphing these is what they're getting at. The slope is what we care about. And the other name that we're going to hear for slant line is oblique line. So it actually has a slope that's not 0, is what we're saying. That it is a linear function. So example 2 says we're going to find an equation of a linear function. Write an equation for a linear function of f such that f of -1 is 2 and f of 3 is -2. And what on earth are they talking about? Well, they just gave us 2 points, is what they did. They said if you put a -1 into this function, you get a 2 back out. And if you put a 3 into this function, you get a -2 back out. Well, now we know what to do. Because what we do next is find the slope. And that's going to be the change in y over the change in x. And notice I'm using the Greek symbols here. When you get to college, nobody writes y sub 2 minus y sub 1 over x sub 2 minus x sub 1 over 1. It's always change in y over change in x. That little triangle symbol is called a delta symbol. And it just means change. So we do the slope like we normally would, but instead of writing down each little detail of the formula, just do change in y over change in x. So negative 2 minus 2 would be negative 4. 3 minus a negative 1 will be 3 plus 1. We get a little slope there equal to negative 1. Now, we have 2 points to choose from, and we have a slope. We're not going to slope-intercept form. We don't have the y-intercept. We go to the formula that fits best for the information that we have, and that would be point-slope formula. If you remember this one, I'm going to just start writing it down. Beautiful. Got it. So, does it matter which point we pick? No, it doesn't. I generally like to use the smaller numbers, I guess, less mistakes maybe. So y minus a negative 1 will be y plus 1 equals negative 1 times the quantity x minus 2. Usually, textbooks will give the answer in slope-intercept form. Here's why. Obviously, if I didn't take negative 1, 2, I would be using this instead. Like so. Oh, did I reverse them on this one? I did, I reversed them. There we go. Both of those are right. Both of those equations are right. It's just that what we have to do is be able to check it in the back of the book. So usually they'll take it all the way down and put it into point slope formula. So y minus 2 equals negative x minus 1. You add the 2 to both sides. And you're done. And with the blue one as well, it's going to come out to be the same thing. So even if we chose different numbers to put into the formulas, we would all end up with the same answer. And that's usually what they'll do in the back of the book. Unless they specifically say, write this in point slope form. Done. You know, you just plug in the numbers and you walk away. So this says verify graphically and confirm numerically. Well, we want to see that our line truly does go through the points that they gave us. So we'd probably just take a second and slap it into the graphing calculator and make sure that our table shows the points that we had. So our points were negative 1, 2, and 3, negative 2. Because if we just make this by hand, we probably aren't going to see all the points unless we're very careful. Usually by hand our intervals will be a little bit off. So this one would start at 1 because there is our y-intercept back there, and then down 1 into the right one. And like I said, if we're really careful, maybe we could pick this up as negative 1, 2 and 3, negative 2 over here. Or we could use our slope backwards and make sure that that's going to hit there. But confirming numerically means, hey, if you said this is your formula, and let me rewrite this as f of x. If you're saying that's your formula, when we put negative 1 in there, we better get a 2 back. And when we put 3 in there, we better get a negative 2. So verifying numerically just means plugging it in. So this would be 1 plus 1, which is 2, and negative 3 plus 2, which is negative 2. Yeah, we verified it numerically. It definitely works. So I wouldn't have had to write this version out right here. Why not? Look at the instructions. Why would I not necessarily have to put Yeah, it said we're finding an equation of a linear function. So there's the rub. You could get away with y equals and say, hey, it's a linear equation. The mention of function kind of says, yeah, they really want the f of x, but we would take either one in this case. You know, it doesn't matter because it is pretty, well, it's telling us both things. So it's kind of messing with our head a little bit. So next up would be the important part of this, which is finding that slope. You know, that was kind of the first step as we went through this. And it is average rate of change. That's what it is. So another property that characterizes a linear function is its average rate of change. The average rate of change is, of course, the difference between the two y's over the difference between the two x's. An average rate of change is really just slope. You know? So don't let the average rate of change, or sometimes they just say rate of change. Don't let that throw you. It's slope. It's what it is. So this is why earlier this year I had mentioned the slope. Find the slope, average rate of change. y2 minus y1 over x2 minus x1. And that is not because I didn't think that my exponential students couldn't remember y sub 2 minus y sub 1 over x sub 2 minus x sub 1. But this is the part everybody forgets when it comes to the MCAs, that average rate of change. So if we can just get it into our head, average rate of change is slope, then we won't be sitting there thinking, I know I'm supposed to know how to do this problem, but average rate of change, I just can't remember what that means. So constant rate of change, a function defined on all real numbers, is a linear function if and only if it has a constant non-zero average rate of change between any 2 points on its graph. So it has a slope that's not zero is what they're saying. And average rate of change and rate of change are the same thing. This happens in a linear function because the average rate of change is constant. And this makes the rate of change the slope. So let's look at this little word problem in exploration. And it says, Camelot Apartments bought a $50,000 building and for tax purposes are depreciating it $2,000 per year over a 25-year period using straight line depreciation. Now, for your homework, this is important. Let's say we know nothing about accounting. How would we know if they just gave us the numbers that this was straight line depreciation? Well, this is 50,000, and they're going to depreciate it 2,000 per year for 25 years. How much is $2,000 a year for 25 years? 50,000. So what they're doing is they're just taking the time period and they're dividing it by how many years they're going to use it and using that for the straight line depreciation. It doesn't change, like some depreciation for tax purposes will say for your computer, the first year you can depreciate 50% of your computer cost. The next year you can depreciate another 20% and the next year another 10%. But this is just, hey, every year you're going to do the same thing. So it says, what is the rate of change of the value of the building? So basically, what are they doing to this every year? What's going to happen to the value of the building at the end of the year? Be 2,000 less. That's our slope. Negative 2,000. It will be 2,000 less than it originally was. 2 says, write an equation for the value v of t. So they don't want us to use x, they want us to use t. Of the building as a linear function of the time t since the building was placed in service. How much was it worth when it started? 50,000. Bless you. To depreciate it, are they adding or subtracting to that value each year? Subtracting. Do we know how much they're subtracting every year? 2,000. And it is per year. So minus 2,000 t, where that t is the number of years. And then it says, well, evaluate it. Hey, what if v is 0? V of 0. What would we get? Well, that means no time has passed. So it's not depreciated at all. So that'll be $50,000. Hasn't passed none of the time. And then for v of 16, we're saying, okay, 16 years later. Well, let's see, 16 times 2, that's going to be 32. So 50,000 minus 32,000 is 18,000. And I was hearing some people open their calculators. Yeah, you can use your calculator for these. Who cares? You know, you can do that. Solve V of t equals 39,000. Oh, so we want to know how many years it's going to take to get this to be 39,000. It's a little bit of algebra, you know. We're going to do some subtraction and then some division, and you might want to grab your calculator and put it all in at one time rather than writing all the steps out there. But we have 39,000, and we would subtract 50,000. And divide by our little negative 2,000. So it's going to take 5.5 years for that to get down to 39,000. Or 5.5 years. It wouldn't matter in this case since it's a real life word problem. You know, if we do decimals with those, it happens. So that was a little word problem with a line, but you know what? Even the word problems are not too bad. Once you figure out that average rate of change stays constant, and that average rate of change is the slope. That's what we're doing. So the rate of change of a linear function is the signed ratio of the corresponding line's rise over run. That is for a linear function f of x equals mx plus b. Rate of change is slope, which is m, which is rise over run, which is the first thing you learned when you're doing rise over run back in linear algebra. That would have been middle school where they started talking to you about that stuff. And change in y over change in x, which, as I was telling you before, you know, we go from y sub 2 minus y sub 1 over x sub 2 minus x sub 1 to just using the delta symbol. We're talking about the slope. Change in y over change in x. So in the last one, we had this depreciation example. And all they've done here is said, well, let's put the 50,000 in back. I mean, pretty obviously that was the y-intercept because 0 years past, it's 50,000. That's how much this house is worth. So it says rate of change of the value of the apartment building and the exploration, and they just put mx plus b form up here for us to see. And what they've done is they've made a little chart, and it's totally logical. It makes perfect sense that it started at 50,000, and then every year it drops 2,000, and 2,000 more, and 2,000 more for every year. Yeah, because that's what the slope does. You know, the slope was per year, dropping by 2,000. But they're showing us here the change in the year was just 1. So it's going down 2,000 over 1, and there's our slope. Change in y over change in x. So, next up, what do we need to do? F of 0 is the initial value of f. It's the y-intercept, and it is what we get when x equals 0. So in our last example, that was going to be 50,000. Did you have a question on something? This is b for linear functions. So back when we were doing y equals mx plus b, b is what we get when we put a 0 in for x. The constant term, f of 0 equals a sub 0 for any polynomial function is the function's initial value. Why did they make that hard? All you have to remember is wherever there is an x, it would now be 0 because anything that you multiply by 0 is 0. So this is going to be the only thing that's left standing if we put a 0 into the function. So that constant in the back, that's our y-intercept every time. That's going to be your y-intercept. So this means the initial value of any function is the y-intercept in its graph. So, characterizing the nature of a linear function, if we're talking about the verbal, what we want to do is make sure we have a polynomial of degree 1. That's x to the first, nothing higher than that. Algebraic, f of x or y equals mx plus b, where m is not 0, non-zero slope. Graphical, we have a slant line with a slope of n and a y-intercept of b. That's like the quick graph for y goes on supposed to be. You start at b, use the slope to get a point. Analytical, it is a function with a constant non-zero rate of change m. And f is increasing if that slope is greater than 0, decreasing if that slope is less than 0, and the initial value of the function will be f of 0 equals b. Now, I want you to notice something. Look at the analytical type down there. You see how it broke that into every little thing they could possibly say about y equals mx plus b? That's where we go in pre-calculus. We try to get every little thing, every piece of a polynomial talked about so that there would be nothing left to chance. We would know everything that's going on. So we're going to start by something we've already been doing. We've been doing correlation problems. We've been looking at linear regression. So with linear correlation, you're going to collect the data and you're going to take a peek and say, does this look like, in my stat plot, I could use a line for this? And while it might not be a fabulous fit, we want about the same number, that one goes through too many, about the same number of points above and below for a line of best fit. That wouldn't be a bad one. I mean, the points are all reasonably close to that line, so this would be considered a strong positive linear correlation. Whereas if I go over here, now I see that my points are kind of pulling away a little farther on the top and the bottom. So that would be a weak positive linear correlation. And this one in the middle, nowhere to draw a line. I mean, where do you do it? The points are all over the place. So we definitely would not try to use linear correlation with that one. We would say it has little or no linear correlation. Strong negative, because definitely we could use a line to represent what's taking place with those points. But over here, weakening a little bit. We still can see that there's that pattern of negative, but the points are just kind of scattered all over. Now, I will tell you, for all of these in AP Stats, that is not enough points to make any kind of decision, but we're not in AP Stats. So they will give us some pictures and we will have to make some stat plots, and we're just going to do our best judgment call about whether or not we think it can be a line of best fit, linear regression that we should be using for it. Because in the end, our calculator gives us R. And we're going to know that if R is close to 0, we shouldn't have done the linear regression in the first place. You know, a line wasn't a good fit. But if it's close to 1 or -1, we'll know, yeah, the line was good. So correlation strength refers to how well a line fits the data. The direction refers to the slope of the line. So we're really getting a couple of things here. We're talking about strong or weak versus positive or negative. And linear correlation coefficient, that's our R value. It is a number that measures the strength and direction of the linear correlation of the data set. And again, you're going to want to make sure that that R value is on your calculator for the stuff that you're going to do. I think there's one regression problem in your homework. And to do that, some of you have the newer calculators which just keeps it on all the time. But the rest of us have to go to second 0 because that's the catalog of all the wonderful stuff that's in your calculator. And then you have to go down until you get to diagnostics on, because diagnostics is where we get our correlation. And since I was recording today, I wanted to make sure I was using this emulator on the smartboard, but this bugger is slow. And when you get in here, you know, one of the other things to do is to see, hey, wait a minute, I didn't know my calculator could do that. You know, for years, people would ask, can you draw a vertical line on the graphing calculator? And I said, no, you can't draw a vertical line on the graphing calculator. You dig around in there enough, you can draw a vertical line on your graphing calculator. There's a couple of spots where you can make it happen. Just got to dig around in there. So diagnostics on and enter twice, because the first one is just selecting diagnostics on. On the main screen, that's when you execute. So when it says done, you know you're going to see that R value when you're working through your correlation. So, like it says down here, just wanted to make sure that everybody checks that at some point. Having your diagnostics on, seeing that it says done, so you know you have what you need to do the homework and talk about whether or not you have the weak positive, the strong positive, the weak negative, or the strong negative. So here it is in a nutshell. R will be a number from -1 to 1. And when R is greater than 0, we have a positive linear correlation. And when R is less than 0, it's a negative linear correlation. I think that's kind of self-explanatory. When the absolute value of R is about 1, you've got yourself a really strong linear relationship. When your R value is approximately 0, well, if it's 0, then you're in trouble because there was absolutely no correlation whatsoever. But if it's close to 0, weak or no correlation. Two things you probably shouldn't be trying to relate to each other. So, good modeling. Practice depends that we have a theoretical reason for selecting a model. And this is what I had mentioned about that last notes packet, where it said applications and it gave us different situations that we know we should use linear for, we should use quadratic for, we should use cubic for. What they're saying is we shouldn't reinvent the wheel, you know. If there's already been a lot of research done in certain areas and we can just look at it and say, oh yeah, they use quadratics for this. That's what we should do. We shouldn't try to do everything all by ourselves from start to finish. So in business, fixed cost is definitely modeled by a constant function. In economics, demand for a product is a function of its price. So a linear model is used. And down here, we have an example from Twin Pixie. It's down south. There's a lot of Twin Pixie grocery store places. Twin Pixie makes donut-shaped oat breakfast cereal. They sell 15-ounce boxes at various prices over a period of time. That would be Cheerios ripoffs is what they're selling. And modeling and predicting demand. Use the data in table 2.2 to write a linear model for demand in boxes sold per week as a function of the price per box. That makes sense. You know, if they raise the price on the cereal, they're not going to sell as many boxes. If they lower the price, they should sell more boxes. So describe the strength and direction of that linear correlation and then use the model to predict the weekly cereal sales if the price is dropped to $2 or raised to $4 per box. So we want to get a model, which means we need to grab the good old GC here and keep the numbers so I can see them up there. Do you remember where we go? Too long? Stats. The stats button there. Number 1, edit. And I've got stuff in my list. So I'm going to hit second plus, and then I'm going to hit number 4. I'm going to clear all my lists out. But you could also, let me show you the other way. Stats, edit. You can go up to the name and hit clear and enter, and that will take out one list at a time when you do that. But I need to get those prices of oat cereal in here. So 2.4, 2.6, 2.8, 3, 3.2, 3.4, and 3.6. All of them? Yep. And then we go over to list 2, and we'll put in the amount of boxes that they sold. So 38,320, 33,710, 28,280. 26,550, 25,530, 22,170, and 18,260. And definitely, especially with this one, because it's kind of clunky, double check that those numbers all came out correctly. Looking good. So I want to do my linear regression. Stats, arrow to the right once for calculate, number 4. And now this is where everybody can see it in the screen. So, some of you don't have this list. Who doesn't have this list of stuff on the screen? You're going to have to do this. You're going to have to hit second, number 1, because that makes list 1 show up, comma, and that's right above the 7, second, list 2, comma, and then hang in there a minute because I'm going to show you how to get this stored into the y equals. But for the rest of us, we're going to make sure that this says list 1, enter, and that this one says list 2. Again, you hit the second button and then go from there. The frequency list, we couldn't care less about that, but we want to store this so we don't have to do a lot of by hand math. And where we want to store this is y sub 1. So we're going to go ahead and everybody is going to put y sub 1 in there. Now, some of you already have list 1, comma, list 2, comma. Let's all put this y sub 1 in there. So that's going to be variables, which is right to the left of the clear key. It's right to the left. It is to the left of the clear key. And we want y variables up here. For functions, number 1. And then we'll just put it in number 1, y sub 1. And down to calculate and enter for this calculator. Those of you that don't have that screen, just hit enter at the end. And there it is. What do you think? Pretty decent line of best fit? Yeah, 0.981. That's not too bad, huh? Now here's the better news. Hit y equals. Decimals and all. You know, we don't have to retype that in there or anything. Everything went right in there. So let's see what they wanted us to do with all of this. Find a model using your GC. So our model, which mine is covered up now, would have been, I'm going to use D of X for dollars, negative 15 point, oh no, it was negative 15,358. 0.929x. Plus 73,622. 5. Got it. And our R value was about negative 0.981. So now, describe the correlation. Well, it's strong. 0.981 is really close to negative 1, but the negative tells us it's a strong negative correlation. So we get 2 pieces out of that. And then it says, use your model. Okay, well, they wanted to know if the prices drop to $2, how many boxes would they sell? And if it's raised to $4, how much would they sell? So here's what I'm going to do. I'm going to cheat. I put it in there as y sub 1. I should be able to just go to the table feature. I'm picking up the wrong calculator. And do second table. And take a look at what's in front of what we have here with the 2. Well, when x equals 2, we've got 42,905. Come on, catch up now. There we go. And then with 4, 12,187. Now, if you're worried, well, where's my decimals? I'm always supposed to go to 3 decimals. What did the y stand for? X was money. What was the y in our original table? Boxes of cereal. We're not going to put 0.738 boxes of cereal down. We're not going to do that. So we can just use the table feature and we can get what we need. So this was 42,905 boxes. And this one was 12,187 boxes. So let's be business people here. Does it work out nicely for them if they sell at $2 a box? They're gonna sell a lot of cereal, aren't they? Does it work out okay for them if they're selling $4? No, they're not gonna sell a lot of boxes of cereal, but the price is higher. So in the end, things are probably gonna even out for them. But that's our interpret your answer, but that clanking makes me worried that I'm reading the text. Okay, so we would write ourselves a nice little sentence here about at $2 about $2 for each box of cereal, Twin Pixie would sell about 42,905 boxes. At $4 for a box of cereal, they would sell approximately 12,187 boxes. So this is the little blah 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 sentences thing here. And last but not least, regression analysis is what we just did. We're going through and finding all this good stuff. You enter and plot the data in the scatter plot. Find the regression model that fits the problem situation. Superimpose the graph on the scatter plot and observe the fit. Use the regression model to make the predictions called for in the problem. There's one more thing I wanted to show you, just because we had said we were going to show people how to do this. I actually think this is kind of a silly little feature. But if you go up into second table set, we've done this before where we said, hey, let's just change that to a different number and change it to a 2 and look. But this stuff down here, you can actually let the calculator ask you which X you want. So if I change this independent variable, the variable that I'm putting in to ask, when I go to the table, it freaks me out a little bit because there's nothing there until I tell it. I want the 2 boxes. I want the 4 boxes. I want the 6 boxes. So the table shows up normal if we just leave it on auto. But if we change that independent variable to ask, it's waiting for us to tell it what to put in. That's what we're doing now. All right, like I said, the table feature works really nice anyway, so that's something I really don't use very often. So, lots of review. Do you agree with me today? All this correlation stuff? We definitely tackled a whole lot of objectives today. But section 2.1, day 1, page 169, we'll do some jumping around, just getting the things that we covered today. 1 through 18, 47, 49, and 51. And I have a little hint up there. In 13 through 18, you're going to get messed up because they didn't go by ones for the scales. So know that. When you're looking at their pictures, know that they did not go by ones, and then I think you'll be okay if you think that way.